Do we have picture yet? Results, I still need to collect more data. Results not produced yet. Yeah. I'll let you know afterwards. Okay. Power, is it not? Is it powering up? Is it?
It's blinking green.
Okay, well, come on.
Just wait till
No, I can't wait. Come on.
It's solid green now.
Oh, okay. All right. So, last lesson we were looking at the Z variable, and we were calculating the likelihood of it having different values. So, of course, as you were asking me, the Z doesn't represent anything in real life, really, because in real life you'll have situations like this. So, for example, you might have a collection of data on students' heights. So perhaps you discover that most people's height is, let's say, 160 centimeters. And maybe you also discover that the standard deviation, this is the average, mu, and standard deviation is maybe 5 centimeters. Yeah? So, how many people will be less than 160 in this picture? 50%. And how many are more than 160? 50%. So you can actually use these distribution graphs for calculating probabilities of things like height. So for example, if I asked you a question, how many people will be between the heights of, say, 160 and 170? Well, it's the same as what you did before. You mark off 160, you mark off 170, and you calculate the area. Same idea as previously, yeah? But here's the small problem. You watching? Come on. Sorry. Don't make me move you as well, please. No, everybody gets one chance. Okay.
No chance.
No, trust me. No, trust me. You did. Okay. What was I saying? Oh, yeah. Listen, don't make me move you further away, okay? Now, the problem here is you don't have a table in your formula book for every possible situation, right? The table you have in the formula book is exactly for this situation, where you have an average of 0 and a standard deviation of 1. That's the one in your table book, okay? So what we need to learn today is there's some way to change this problem into a problem we did in the last class. Now, before I continue, I just really want to stress that this is a very, 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 very common distribution for data. If you collect any data and draw the histogram, it'll probably have this shape to it. Think about that histogram you did with Colin, the pollen histogram. What shape was it? Do you remember? Did it have a shape where it rise and then fell? Yeah? Yeah. Well, I'm just drawing it roughly, yeah. So it did have a rise, a peak, and a fall. Yeah? What I'm saying is, most data you'll collect in science will have this shape to it. Okay? Most data. Pollen count, height, weight, measuring acid, base levels, all this type of stuff. So, how do we convert? Just before we do that, just a bit of notation. So we call this graph, this variable 0, 1, n01. And we call this one here n160, 25. And the reason for 25 is we put the variance in here, which is 5 squared. So, just to make it crystal clear, if I have a graph like this, and its average is mu, and its standard deviation is sigma, we call this n mu sigma squared. Yeah? It's just notation. It's just notation. I mean, you don't have to. You could just simply say it's normal with average of 160 and standard deviation 5. Like, you just literally say that. Okay, so I'll scroll down now in a second and we'll look at the way of converting between the new graphs and the one we have in our formula book. Yeah? Can I scroll down? Okay, so, yeah. I'm only drawing them very roughly. Try to draw them flat, rise to a peak, and then fall back down. Just roughly. Okay, can I continue? Yeah. Right, so this is the trick. You have a distribution, and it's centered at mu and standard deviation 0. And if you want to change it into a distribution like this, there's x. And you want to make it have a 0 in the middle and a standard deviation of 1. You use a formula called the Z transform. And the formula is just Z equals your x minus your mu over your sigma. That gives us the location of the Z in the new graph. Now, I'll do an example now. So this is the Z transform formula. It lets you change to any graph to the one that's in the formula book. There's no chance that you have that pollen histogram with you, is there? Does anybody have that pollen histogram with them? You do? You have it, yeah? You can just pass it up. Okay, let's have a look here. Thank you. So this is interesting. Pollen grain, is it? I cannot read. Oh no, I can see it now. No, I don't like it. Send it back. Thank you. I'll make up my own one, thanks. Can I scroll down to an example? Okay, here's an example. You've probably all heard of the IQ score. So what's interesting, like with most things, IQ has a normal distribution. Most people are, well, it's actually, the test is designed so that the average IQ score is 100. And it's also designed so that the standard deviation is 15 points. Okay? So you might ask a question like, what's the probability that a randomly selected person will have an IQ of 120 or less? So that means you'd want to calculate this. Here's an IQ example here.
I think I've got some examples for you.
Of which one?
It's something different.
Oh, that's okay, that's okay. I wanted to use something from your biology class that you did.
This is the resolution.
It's from, did you do it with column? No, I wanted something you did with column, so it's okay. Right, so here you would have to convert this into the old graph we were using. So the old graph is centered at 0 and its standard deviation is 1. But this point here, of course, is not 120. Let's convert it. So the rule is Z equals the point you want to convert, 120, minus the average over the standard deviation. So what's that, 1.3? Yeah, it's 1 1/3, is it? Like this. So what value do we look up in our formula book? Yeah. 1.33. So, you have this answer now. The probability that the IQ is less than 120 points is equal to whatever the table book value of 1.33 is. And what is that, by the way? 0.82. So that's roughly 91 roughly percent. Do you see how useful this is? Because you can ask any question like, how likely is it I'll get between blank and blank? And you can get an exact number for this.
But not all histograms look like that.
No. But the vast majority do. Especially in a science context. So, is it from the histograms there?
Yeah.
Which one? Yeah.
If you were to see this one, would this apply to it as well? If
No,
it,
it
doesn't go all the way?
wouldn't. No.
No,
This
that's
is,
if you click just the first half.
Oh, well, I suppose, but you're not really able
It's
to do
not
that.
going down all
No.
the way.
It needs to be at least this shape. Although this is better. This is, yeah. Interesting. Yeah. We don't concern ourselves with too much of that stuff. It's a bit more, yeah, because it's AP,
Yeah.
so it's more advanced. Okay. Can I scroll down to another example? Do you have this one? Yeah? Okay, so like I said, IQ is a good example. Also, height is a good example. Now, really, in real life, you should look at height for one particular gender, because if you mix your data, the histogram would look more like this. And the reason for this is actually because the average height really depends on the gender. So it's better if you can split your histogram. So for example, maybe you just look at the behavior of the height of the male students in a population. So that would follow your normal distribution. I'm not sure, we'll just make up a number. We'll say the average is 165 centimeters, and the standard deviation we'll say is 10 centimeters. And that's our average. Now, I give you a chance to try it, because I think you might be able to get it. My question is, what is the probability that you pick a student and their height, we'll say, is more than or equal to, let's say, 175 centimeters. So how likely is their height more than this? Okay? More than 175. Okay. You got an answer nearly? So what should I do first? Yeah. You can convert it first if you like, or later actually. So if I convert this into the normal 0, 1, then my 175, which is this, it won't be 175, I think it should be 1, is it? Yeah, it's 1. So it's 175 minus 165 over 10. So you need not to look up 1, because 1 would give you the area to the left. So what would this equal? It'd be 1 minus, you look up 1. So what would that be? 8. 8 what?
It's a 1,
1587. Yes.
16%. 16% of people will have a height more than 175. Seems reasonable. What? Seems reasonable. Right? You don't know which country I was in when I collected this data. That's the other thing too.
Take it like 165 is
Yeah.
50%.
Yeah?
175 is 16.
I don't know what you're saying, man.
More than 165, the
More than 165 is 50%. Yeah? So?
175 is 16%.
Yeah.
Don't know how many
Yeah. 50% of people are taller than 165.
Okay.
So more than 175 should be smaller than 50%.
There's 34% between 165 and 167, right?
34% between 165 and 175. Yeah. Yeah. Yeah.
From what I'm looking at building block exams, you could basically use this product not histograms that look like this.
Yeah. Yeah.
Not, like for example, let's say if it just goes down at 175, or if it's a little bit narrow, you know what I'm talking about?
You can still use it as an approximation though. As an approximation you can use it.
So, for example, let's say you take 10 people, the lowest was 150, the highest was 170, the middle okay would be 160, but
Yeah, that's a bit different though because it's only 10. It's too small. It's too small. You need really to make an accurate histogram at least 30.
1,000, the lowest,
Yeah.
1,000, the lowest was 150, the
Yeah.
highest was 170.
Yeah, no, I understand. No, I understand. Look, technically speaking, this graph doesn't touch the x-axis, right? So that means technically speaking, there's a probability that somebody would be 10 meters tall. Obviously, that's wrong. It's an approximation, but it's extremely accurate approximation. So maybe in real life, it's not 0.1587. Maybe it's 0.1527. But so what? It's still about 16%. You know, it's only an approximation. It's not exactly representing real life, but it represents it really, really well. Let's look at another example. Make it a little bit harder now for you. Let's look at what else? What else have you measured in biology? Pollen count is one thing. pH.
The average would be 7.
Okay. pH is 7. Okay, let's say pH 7, and we'll say the standard deviation is 1. Okay, my question is there any interesting range on the pH scale? Like if it's between these two values, it means it's a blank or anything like that. 9 and 14.
Or like 8 and 14 is alkaline.
Is it 8 and 14? Okay, well roughly we'll say 8 to 14. Okay. This means your sample is an alkaline, is it? Okay, so that's a good question. Calculate the probability that the sample is an alkaline then. Try that. By the way, I don't actually know what the standard deviation is for pH. I kind of feel like 1 might be too small.
Yeah, no, I think it's too big.
You think it's too big? Okay.
Or it might be a bit too small.
Maybe it is.
Things are usually around the basic, like 7.2, 7.3.
Are they? Okay.
Or a little bit less, like 6.
Most values are between 6 and 8 then.
A lot.
Okay, well then, yeah, no, 1 then would be okay. Then 1 would be okay. be a pretty big number, I think. What, did you get an answer?
Maybe between 30 and 40.
What's the question again?
Calculate the blue area.
That's the last
Did you got an answer?
I'm not sure who I
It's just
Sorry.
Same thing, identical.
So,
Where you were going for that?
kinda, because of the choice here. This is 0. I have to mark off 8 and 14. Now, if we convert 8 minus 7 over 1 is 1. And then don't forget you have to do 14 as well. 14 minus 7 over 1 is 7. So if I want this area, what do I do now? Table value 7 minus table value 1. Now what is the table value of 7? Yeah, so what's the biggest value they have?
3.9.
And what is the area for 3.9? 1. So basically, once they get to 3.9, it's always 1.
Okay, so 7 is 1.
You can take it to be 1. Technically, it's just rounding up to 1. So this is 1 minus 0 point, what's this value?
It's the same thing as the
8,
8413.
8413. Okay, so it's about 16%.
I
Yeah.
just want to ask about
No, leave me, I'm tired.
please.
No, later, I'm tired. I don't have any coffee in front of me.
Let's go.
90% of my energy right now is being used to keep me awake. Only 10% is actually thinking about maths. Okay? Maybe even less.
And what's Dan thinking about coffee?
Huh?
You're still thinking about coffee, aren't you? So then that's like a good 7% of our knowledge.
The coffee?
Like a good
I use your energy to make
So for the second graph, what's the standard deviation?
Right now, a lot of people who are talking, I don't actually hear their words because I'm not fully awake. So I hear people talking, but yes,
For the second graph, what's the standard deviation?
still
Still 1.
1. Yeah. Okay, can I do another example? Yes? What? I'm very tired. Very tired. But you have an advantage, okay? If you got tired, you could fall asleep. If I fell asleep during teaching, everybody would notice. Okay, let's have a look at another one. So what else have you measured recently in chemistry or biology? So you've done pH, we've done height. Anything else? Like for example, in chemistry, have you not measured anything in the labs? Temperature and weight. Yeah. Okay. Well, let's do weight as an example here. So let's say let's say we're measuring the weight of samples from an experiment. So you measure them, and you notice that they have an average of, let's say, 10 grams. And let's say the standard deviation, we'll say, is 2 grams. Okay. And you would like to know how much of a chance is there that the weight will be between 6 and 7 grams. So you want to calculate this probability. So I want the probability that the mass is between 6 grams and 7 grams. Okay, let's calculate that now. what does 6 and 7 become?
12 and 13.
12 and 13? No.
12 and 13.
Minus 2
No.
and minus 1.5.
Minus,
2
yeah,
and 1 minus 1.5.
minus 2 and minus 1.5. Okay. That question?
How do you get minus 2 Use the formula.
6 minus 10 over 2 and 7 minus 10 over 2. Yeah?
Yes.
So this is equal to minus 1.5 minus 2. And then, yeah, you know the story now. 1 minus 1.5 minus 1 minus the 2. They cancel, the ones cancel, and you're left with 2 minus 1.5. So what did that work out to be? Give it to me as a percentage. 4.4%.
I got 3.9.
Come on, you just have to look up two numbers and subtract. Who's right, who's wrong? Who else has an answer for this?
I'm pretty confident about it.
Well, you're being outnumbered. I have two 4.4s.
I'll try again to be the focusing one.
Yeah, okay, sorry, it's outnumbered 3-1 now. Continue?
Oh, yeah.
Continue? Yeah.
I thought it was
Right. Let me scroll down a little bit here. So, these questions I've done so far, they're pretty straightforward, all right? You know, there's nothing too crazy about them. I think you can all see they're quite short. So what I've done so far would be a section A question. 3 marks, 4 marks, something like that. Now let me give you a hard section B question, okay? So you have some histogram, and it has a mu and it has a sigma here. However, I don't tell you what the mu and the sigma are. You don't know what they are. What I do tell you is this. I mark off a point here. Let's just say it's 8. And I tell you that this area here to the left of 8 is 0.1. And then I mark off a point here, 11. And I don't know, let's say this is 0.2. So this is quite tricky, but I think some of you might get it. We have to work out what was the original mu and sigma. So look, I know it seems hard, but you go through the same process. You first have to convert the 8 and 11. The only difference is you have a mu and a sigma in your answer, okay? So when you convert, I'll get it started for you. This will be 0, and what would this one be? It would be 8 minus mu over sigma. And this area is still 0.1, okay? Now, okay, so that's it started. I'll let you try and continue. See if you can work out the mu and the sigma.
0.1 is the answer,
Yeah, the area. And it is in the correct position. 8 is less than mu and 11 is bigger than mu. You don't think so? Maybe I chose bad numbers. Let's calculate it. You think you can get it?
Yeah.
Okay. Okay. We'll see. So obviously whatever answer you get for mu, the average, it should be between 8 and 11. You got an answer?
Yes.
Did you get the right answer?
Yes. I think this one looks a big one.
What'd you get from mu?
You is this
Yeah, the average, yeah.
use the average.
Mu could not possibly be 7.
I got 5.
It could not possibly be 5.
Must between.
It must be between 8 and 11. Has to be.
Wait,
Can I check your data, please?
Hmm?
Can I check your data?
Well, I'm going to do it now.
are you sure it's correct? The values you gave?
What is small?
Yeah.
Are you just throwing?
Huh?
Oh, 1 second.
Huh?
3.
That's even worse.
The standard deviation above plus 30. Yeah?
Ah, no. No, no, no.
Two
no.
people with the exact same values.
It's amazing how many people can be wrong, isn't it? Yeah. Let's have a look at it now. So, we'll have to convert the other one here too. So this will be 11 minus mu over sigma. And this is 0.2. Now you know, if you were to look up the table book value of 8 minus mu over sigma, you're supposed to get 0.1. And if you look up the table book value of 11 minus mu over sigma, you're supposed to get 0.8. Okay? Now please check your table book. What value do you need to look up so that you get... Oh, no, stop. So the problem here is 8 minus mu over sigma we know is a negative because it's to the left of 0. So we can fix that by doing 1 minus table book mu minus 8 over sigma should equal 0.1.
Sir, why is it 0.8?
Because the table book gives you the area to the left. So if you were to look up this value, you should get 0.8. That would correspond to 0.2 on the right. Okay. So table book value mu minus 8 over sigma equals 0.9, and table book value of 11 minus mu over sigma equals 0.8. Now, back to the table book. What value do you look up so that you get an answer as close as possible to 0.9?
1.3.
Is it 1.3 exact?
No, 1.2.
1.29.
1.28.
No, 2.8.
29. 1.28.
2.8 is 0.87.
Okay, 2.8. What else? Okay. And what do you look up here to get an answer of 0.8? 0.85. So,
No, 8.4.
No,
84, okay. Alright, so here's the key trick step here. If looking up the value of 1.28 gives you an area of 0.9, then it must be that this was the 1.28. So mu minus 8 over sigma must have been 1.28. And likewise, 11 minus mu over sigma must have been 0.84. Now, what type of problem does this look like? How many equations do I have? 2 and a half. 2 variables. So, yeah. Simultaneous. So, let's solve this. Mu minus 8 equals 1.28 sigma. 11 minus mu equals 0.84 sigma. So mu equals 1.28 sigma plus 8, and 11 minus 0.84 sigma equals mu. So we can 1.28 sigma plus 8 equals 11 minus 0.84 sigma. So that's 3. And then what's that? 1.28 plus 0. What is it? No, plus 2, 3, 1.32, is it? 2.32, is it? Guys, is that right? 1.28 plus 0.84, what is it, please?
Yeah, it's
2.12.
2 point... Guys, stop.
2.
Just tell me 1.28 plus 0.84.
2.12.
2.12. Okay. 2.12 sigma equals 3. So sigma is 3 over 2.12. So what's that? 1.4. Now we can just sub that back in to get mu. Mu is 1.28 times 1.4 plus 8. What's that?
So,
Yeah.
why did you do mu minus the 8 and 1 minus mu the first step? Remove the
Here,
yeah,
I flip the sign because I use the trick. The trick that says if you look up a negative, then that's 1 minus the positive of it.
then 11 also take.
So 8 minus mu flipped around to mu minus 8 by changing the sign. What's the mu?
9.8.
9.8. So, we've worked it out. If the average is 9.8, and the standard deviation is 1.4, then 10% of the data will be below, what did we say? 7? What was in the original? 8. That's 10%. And then, what was marked off here at the upper end? 11. How much is more than 11? We said 20%. I think I said, didn't I? Yeah. So not 5, not 2, 9.8.
I said 10.
No, I said segments.
You said what?
The segment.
Far from
Also,
the
you said count.
I had one issue. I didn't get what 0.1 and 0.2 are. I thought they were divided.
No, the area. The answer in the formula book.
I thought that's why I instantly put it in the middle. Which they gave to us.
Yes.
But did they specify what 0.1 and 0.2 are?
Listen. I know I'm tired, but I think I'm still speaking English. This is what I said at the start. This is an example of a hard section B question, whereas the previous ones I've been doing are examples of standard section A questions. My point I'm making is, if you could do this question, then really you can do any question, because this is the hardest it could possibly be. It can't be any harder than this. Now what they sometimes do is they give you one that's a little bit easier than this. A typical example is, in the original question here, they might tell you one of these, and then it's no longer a simultaneous problem of two equations, it's just one equation. Okay? So this is the hardest, but still possible for the exam. But still, you know, the hardest one you could get in the exam. Yeah? Did you write this down? Come on, guys. Did you write this down? Amjad, did you write this down? You're right. You all have this? So, about the exam for this. No, listen in. This is one of those questions in the exam which I always think students should answer quite well, but it's not answered as well as I think it could be answered. And I'm not sure why. I think it just comes from a lack of practice. Because this one true, it was very, very hard. But the previous ones I did were quite short. You know, these are not exactly big questions to do. So I often get confused about why students don't get full marks in this question in the exam. So I really think it's probably because they don't practice enough. Because some of you maybe have not studied this topic before. So, I mean, I have 24 questions there. Yeah, well, I'll just tell you though. 1 to 20 would be possible exam questions. Now, 21 to 24 is too difficult for the exam. But if you need to practice more, you could try for 21 to 24. In fact, guys, like, just so you know, 1 to 20 is an exam question. However, 1 to 6 is actually too easy for the exam. So the difficulty range for the exam would be questions from 7 to 20. That would represent exam question difficulty. Okay? So you've got a couple of minutes left. You should get 1 or 2 of these done now, please. No, do the questions now. No more questions. No, do the questions. Sit, do the questions. Less questions, more doing.